all of everything you've seen so far and everything you're about to see were all created by NVIDIA's creative organization. My first demonstration for you today is the holodeck. Christian, first of all, tell us about your car. So this car is a hypercar. It's a V8 twin turbo with 3 electric motors in it, right? So take it from there.
Yeah, so this is our latest creation. It's a hybrid car with direct drive, no gears. We have a combustion engine with up to 1,200 horsepower, one of the absolute fastest cars ever produced for road use, and something I'm very proud of. And seeing it in this environment is just amazing. Trying out this system with you guys really changes the view of what's possible, how to create the cars and showcase them during the building process. It's just fantastic.
Look at that. Isn't that amazing? But what if I want to see like all the parts? I just want to do an inventory of the parts. Okay, you guys, thank you. Thank you very much. All right, enough fun. It is just so amazing to be in these environments together with all your colleagues, and you're talking to each other, and you're pointing at the same thing, and because you could touch things, you could actually lift things up. And because you're in that environment and you're superhuman, it reacts to physics, but you can lift up amazing things. And so the holodeck is such a great place. In our company, we do a fair amount of deep learning research. Let me give you an example of what's actually happening here. Basically, this network in the middle, this is just an articulation of the network, it's called an autoencoder. We're asking this network, if we gave it a distorted image of that, a noisy image of that it has to learn how to generate that image, the beautiful image, from that noisy image. The way that it has to do that, it has to figure out how to recognize the important features and eventually generate it automatically. Now, one of the areas we've applied this to is ray tracing. Ray tracing, as you know, is computationally incredibly intensive. Following photons around as we try to regenerate an image is very computationally intensive. And so one of the things that we decided to do is, what happens if we were to teach a network to fill in the spots that we haven't rendered yet? Okay? To generate some of it and to automatically infer or to use artificial intelligence to decide what to fill it in with. And so let's take a look at that. This is our ray tracer with deep learning. On the left, let's see. On the left here is without deep learning. On the right is with deep learning. Notice how noisy it remains for some time. With deep learning, it figured out, based on the surrounding things that it has already rendered, and based on recognizing what objects look like, what paint looks like, what glass looks like, it's learned those things, and it's selected the right picture, selected the right colors to fill it in with, all by itself. And as a result, you're able to take this noisy image and turn it into a beautiful image. The implication is actually quite amazing. We can now get distorted input from the sky, from the internet, and somehow we could have a network running here that regenerates what it's likely to be. Okay? Autoencoders, using deep learning for computer graphics. Ladies and gentlemen, I would like to introduce you now to the next chapter of computing. Ladies and gentlemen, the Tesla V100. This is reticle limits. Reticle limits basically means that it is at the limits of photolithography, meaning you can't make a chip any bigger than this because the transistors would fall on the ground. Every single transistor that is possible to make by today's physics was crammed into this processor. 21 billion processors, almost 100 billion vias, little connectors, 100 billion vias. To make one chip work per 12-inch wafer, I would characterize it as unlikely. And so the fact that this is manufacturable is just an incredible feat. 800 millimeters squared. If you guys have an Apple Watch on your wrist, the die size is approximately like that. Okay, so just take a look at your Apple Watch, gives you a feeling for it. 5,000 processor cores in here, 7.5 teraflops of 64-bit floating point, 15 teraflops of 32-bit floating point, and a brand new type of processor. A brand new type of processor called Tensor Core, which results in 120 teraflops of tensor operations. 120 teraflops. And we're utilizing the state-of-the-art, the fastest memories that the world can make today. It's made by Samsung. Our partnership with them is terrific. The two engineering teams have been working so closely together, pushing the limits of how fast we can drive memories. And we've been able to achieve 900 gigabytes per second. It is just so fast. And then lastly, the second generation NVLink gives us 300 gigabytes per second, basically approximately 10 times the fastest PCI Express in the world today. So we created, for developers, the DGX-1 supercomputing appliance dedicated to AI. With Volta, it has almost, I wish I just had 40 teraflops more, because it would have been wonderful to say. 960 tensor teraflops with 8 GPUs inside. It can now take what used to take 8 days on tight next to train, now literally takes 8 hours. What took a week now takes a shift. And it replaces 400 servers. Because Volta is not quite ready to ship now, it'll ship very soon. It'll ship Q3 and DGXs and Q4 from OEMs all over the world. For anybody who places orders today, starting today, you'll get a free upgrade to Volta when it arrives in Q3. We've been asked so many times, would it be nice? I don't have a data center, and I don't have cooling. I'm a startup, and I've got 10 engineers. And what we need right now is to get working on deep learning. Could you please make us a small version of DGX? And so we thought, well, that's an interesting idea. So we prototyped up a few inside the company. And of course, putting that much computing power next to an engineer, you really, really have to keep it quiet. So we liquid cooled it. And it's whisper quiet. You can't hear it at all. One of the things that we did was we partnered with Microsoft to create the industry's first industry standard hyperscale cloud graphics accelerator. Notice there's a 1U computer underneath the server. And there's these 4 cables that come out from the base computer into the HGX-1. And these cables are basically PCI Express. And it allows us to configure this server in 2 CPU and 8 GPUs, 2 CPUs and 4 GPUs, 1 CPU and 2 GPUs, and so that they could provision all kinds of different size services to the market. And of course, we still have the ability to virtualize the GPUs so that many instances can run on 1 GPU. Ladies and gentlemen, this is Tesla for hyperscale scale-out. This is what we call the PCI Express FHHL, the sexiest name ever. Full height, half length. 500 nodes is basically this entire row of servers. And so 500 nodes translates to basically $1.5 million, not to include all the cables and all the power delivery and the cooling, et cetera. And it consumes 500 watts each, so 250,000 watts, 250 kilowatts. Well, if we used a relatively conservative number of about 15x reduction, that basically translates to 33 nodes of this. That translates to 33 nodes. That's the savings. Instead of 500 nodes that occupies an entire row, you can replace it with 33 nodes, or you could increase the throughput of your data center by 15 times and not have to build more data centers as AI workloads floods into hyperscale data centers. We've created a platform we call the NVIDIA Drive, and basically it's a roadmap, it's an architecture that spans level 2 to level 5, from augmented driving all the way up to completely driverless systems. We created a full stack. We dedicated ourselves to go solve the self-driving car problem and create the software stack, but open up the software stack. The first thing I'm going to show you is mapping to driving. basically how the car figures out where it is in the world and localize within it and detect everything that's around it and drive. Using the LiDAR, we have a LiDAR mapping car, and we're trying to detect everything that's around us, whether it's the lanes, the vertical poles. We're trying to create essentially an HD map of the structures in the world that we ought to use to localize ourselves later. Okay, so we detect all the road features. The second thing that I want to show you is how we use AI not just for driving, but also to be essentially a virtual co-pilot.
I can now drive you to work based on mapping previous drives. Shall I engage autopilot?
Oh, sure.
Autopilot engaged. Driving to work.
And third, this is a phrase that Gil Pratt at Toyota created that I really, really love. And it's called a guardian angel. Even when you're not driving, even when the car's not driving for you, even when the car's not driving for you, it should be watching out for you. There we go, green light, time to go. Whoop.
Cross traffic danger.
Maybe not.
All clear.
Disaster averted. And so the AI is on all the time, even if it's not in autonomous vehicle mode, it should be watching out for you. We created a new tool, it's a new world, it's a new simulator we call Isaac. Isaac has the input of environments and robots. So we could put virtual sensors of the robot, we put the virtual actuators and the virtual effectors of the robot into it. And when we're done with it, we literally take that virtual brain and put it into a real robot. And this robot wakes up almost as if it was born to know this world. And then the last little bit of domain adaptation that it does is done in the physical world. So ladies and gentlemen, let's take a look at it. This is Isaac. We import mechanical or the environment into it, and we could train Isaac. Now in this particular case, Isaac has been trained. Now one of the things that we could do is, of course, we could replicate a whole bunch of Isaacs and have them all learn. And then we take the smartest one, and we take the brain out of that smartest one, and we put it in everybody else's brain, and then we say, okay, now start again. And then we figure out which one's the smartest one. And we take that brain, we put it into everybody else's, and we say, start again. And so as a result, we could accelerate the time to learning. Thank you guys very much for coming. Have a great GTC. It's great seeing all of you.